So, welcome everybody to another meeting of the seminar. We're going to have today a talk about nearly tight regret bound profit maximization in bilateral trade. It's going to be Federico Fusco from Sapienza, and Federico, the stage is yours.
Okay, thanks. Thanks everyone for being here, and thanks for having me here. So as Galit was saying, today I'm going to talk about this recent paper we had with a great bunch of coders, Simone from Sapienza, Paul from Google, and Chris from Horus, that I think fits nicely in the scope of these seminars, because it will be about algorithmic, it will be about learning, and we will do this for a nice and simple game. So let's start. The problem that we're going to study is super simple and super foundational in economics. And it's this very simple model called bilateral trade, where the goal is to capture the interaction between two agents, a seller and a buyer that wants to trade a good. Both these agents have private valuations and they want to maximize their utility. So they're rational agent, and we are in the middle. We are here, the laptop in the middle that intermediates between these two parties. And our goal is to design a good intermediating mechanism. So let's see what this means. First, what are two natural objectives that we may want to maximize? Well, as it's fairly common in algorithmic game theory, we have two options to start. One is the economic efficiency, namely, we are only interested in the happiness of the system after the mechanism takes place. And here we have two options. So either we want to maximize the welfare, meaning that if there is a trade, so if the item goes from ST to BT, then the final happiness of the world will be BT. And if there is no trade, then the final happiness of the world will be ST, because the seller is keeping the item. An alternative to welfare is gain from trade, that is simply measuring the increasing welfare. So if there is no trade, then the gain from trade is zero. If there is a trade, then it's the difference between the happiness of the buyer and the happiness of the seller. Now, beyond efficiency maximization, one could think, okay, maybe I'm Uber, I'm in the middle, and I want to intermediate between sellers that are drivers and buyers that are passengers. And my only goal should not be only maximize the word happiness, but maybe I want something in return. So in this setting, what makes sense is to maximize profit, or to understand how profit is impacted by this mechanism. And here the profit, a simple formula for it could be, okay, if there is a trade, then it's the difference between what? Between the price that the buyer pays minus the amount of money that I have to give to the seller. So this difference will be my profit. So what the mechanism designer takes in the middle. So bilateral trade was already kind of studied in the seminal paper by Vickrey, but then the big paper, the seminal paper of this area of research is Meyerson and Satterthwaite. Is by Meyerson and Satterthwaite in 1983. So let's see what are the previous results in this line of research. Well, first, there is this surprising impossibility result that states that it is not possible to maximize happiness, so let it be social welfare or gain from trade, without losing money. So this is a strong impossibility result. And another way to restate it is to say that full efficiency is not achievable unless the mechanism kind of subsidizes the market, subsidizes the agent. So this was like the classical economic take on this problem. Then computer science arrived, and as you can imagine, we see an impossibility result. We try to get something good out of it. So there is a long line of research, and maybe you have heard about some of these papers that try to understand, okay, maybe getting the so-called first best is not possible. So full efficiency is not possible, but maybe there are simple mechanisms that achieve a constant factor approximation of it. And actually, for social welfare, this has been well known for I think 20 years. While for game from trade, the first constant factor approximation was at stock 22. And all these results that I mentioned are under the assumption that you kind of know the random process underlying this phenomenon. So in particular, what you typically imagine in this, let's say, so-called Bayesian perspective is that you know what is the distribution from which the valuation of the seller and the valuation of the buyer are drawn. So you know it. So this may be joint, whatever, but is known. And your goal is to find an approximation result. From another perspective, the learning perspective, there has been some work in trying to understand, okay, what if I don't know the distributions, but I have to repeatedly interact with the environment to get something out of it? And there is a recent long line of work along this line where they have a very strong characterization. Let me point to this super recent Soda paper that kind of closed let's say, all the natural gaps that were in this research. But still, all these works were about efficiency maximization. So trying to understand how to maximize gain from trade or social welfare, or get meaningful constant out of it. What we kind of asked ourselves in this paper is to say, okay, what can we say about profit maximization? And in particular, what can we say in profit maximization from the learning perspective? So if there are no questions, let's try to get a better understanding of what's going on. So first off, we have seen the setting. There is a seller and a buyer, and we are in the middle. But and we want to design a mechanism. But what is a mechanism formally? Well, with the usual tools from algorithmic game theory, we can just say we can just answer to the question saying a mechanism is just a pair of things. An allocation rule that specifies when the trade happens given the bids of the agent, and a pricing rule that maps bids to kind of the amount of money that the buyer needs to pay and the amount of money that the seller will receive. And what we actually want to enforce is dominant strategy incentive compatibility, meaning that regardless of what the other agent does, we want truth telling to be dominant strategy. And second, to kind of push the agents to participate to this mechanism, we want to enforce ex post individual rationality, meaning that if the seller or the buyer joins this game, they cannot be better off by not participating. Now, these are standard notions. We are focusing on the strongest possible notions. So dominant strategy, incentive compatibility, and ex post individual rationality. And it turns out that under these two assumptions, there is a clear and nice characterization on how the mechanisms would look like. So for instance, an allocation region to enforce dominant strategy, incentive compatibility, and individual rationality has to be, so let's call it north-east closed. What does it mean? It just means that if for a certain point I observe a trade, so I am in the allocation region, then if I move in this direction, so left or and up, then I cannot go out the allocation region. And second, there is also a nice characterization of the pricing rules that are enforced by these allocation regions. Namely, let's try to understand. So if this is the bid, then we have to ask ourselves, what is the minimum payment, the minimum bid that the buyer could have done and still get the item? Well, is this guy here. Okay. So it's the projection of the bid point, of the bids point on the boundary along the vertical direction. Northwest. Yes, you're right. Sorry about it. I always get confused with it. It's like left and right that you never know which one is which. Okay. So this will be the payment to the buyer. And then if we look at the seller, we have to ask the same question, but clearly everything is flipped because now the seller, we want to give him a price that is higher to its valuation, to its bid. So it will be this amount here. So this will be, to use the notation that we're going to use throughout the talk, this will be the payment to the seller, and this will be the payment from the buyer. Yes, exactly. So you see, we started with this game theoretic question, and now we have a nice geometric interpretation of everything. Because a mechanism is just kind of a blue blob that is north-west closed, and the pricing rule is just this kind of function of the projection of the bids onto the boundaries of this blob. So now that we have a characterization, we can forget about bids, we can forget about truthfulness, and just study this optimization problem. And in particular, what we want to understand, we want to learn the profit maximizing mechanism that has, let's say, the best mechanism that has this structure. Okay. So this is the task, our goal for today. So questions here? Awesome. Now, to get some intuition on why this is difficult, you have to think the following. So if the allocation region increases, then you get more trades because more bids will result in a trade. But on the other hand, the boundaries of this allocation region will shift, meaning that the profit will decrease. So there is this trade-off between the amount of bids that we want to result in a trade and the profit that we get out of it. And also to get like some intuition of what's going on, if, for instance, I want to understand with these figures what a fixed price mechanism would look like, so a mechanism that just posts a price and asks the buyer and the seller whether they want to trade for that price, well, this will just be something of this form. So it will be a rectangle, and the angle of the rectangle will lie on the diagonal. Okay, so a fixed price mechanism would be something of this type. And let me mention something that kind of motivates why profit was not so much studied in the Bayesian setting. The fact is that once I give you the distribution, then I can compute the optimal mechanism, the profit maximizing mechanism, by solving kind of a nice LP. So there is a way to kind of massage the distribution in such a way that you have a finite distribution, a finite support, you lose something, and then on this finite support, you just need to find a shortest path on a suitable graph. This is a cute observation, but this is why, if you know the distribution, the problem is not that challenging. Awesome. And the perspective that we are going to adopt to study this learning process is online learning, where that kind of captures other model of learning that you may have heard of, like sample complexity, or also to some extent active learning. That kind of was, let's say, motto is you learn as you go. So you interact repeatedly with the environment. Every time you do something, then this has an impact. And what you do kind of decides what you're going to see in the future. And this perspective now is fairly popular in, let's say, the TCS and EC community, with many nice AGT questions that have been studied. Okay. So let's kind of get our hands dirty and try to understand what is the exact mathematical model that we are going to study. So at each time step t, we are in a repeated setting, a new pair of seller and buyer arrives. The seller has a private valuation ST, and the buyer has a private valuation BT. We do not know these numbers. They're there, but we do not know them. And what we do, we post a mechanism, MT, and we have seen that a mechanism is just a monotone allocation region, because then this clearly induces a payment rule. Then the agent declares STMBT, because everything is truthful. And the trade happens if and only if this pair belongs to the allocation region. And the payments are made accordingly. Now note that in this setting, in order for the mechanism to kind of compute the payment, it needs to know what are the valuation of the agents. And this kind of separates it from other problem in the literature where kind of you have a simpler mechanism and thus it makes sense to study a weaker notion of feedback. Here, we are in, let's say, full feedback. At each time step, you propose a mechanism and you observe the pair STMBT. And in particular, you can compute your profit that then is just computed according to this formula. You get a trade if and only if the pair is in the allocation region, and what you get is the difference between the price paid by the buyer and the price paid to the seller. And note this quantity here can belong to -1, 1. Okay, so it can also be negative. Perfect. Our goal is to maximize the total profit. And in online learning, this is typically done by measuring the regret with respect to a benchmark. And what is the natural benchmark is the best fixed mechanism. So for any learning algorithm and sequence of valuation, we can define the regret as the difference between our performance. So this is us, this is our performance, and the performance of this benchmark, okay? And in particular, we are interested not in general to the regret, but to the worst case regret. So we want to find a mechanism that performs well against any possible sequence of valuations. And in particular, since at each time step, everything is between -1 and 1, my goal is to have sublinear regret, meaning that you're actually learning something, so you're not making a constant error over and over and over. And in particular, if you have sublinear regret, if you divide everything by t, this means that your performance on average is converging to the performance of your benchmark. Okay, perfect. Now, clearly I have to specify the family to which like the input sequence belong. So depending on like the family of inputs that I'm considering, I will get different regret rates. So to recap, in online learning, as opposed to the Bayesian setting, the algorithm has no initial information. And with this model, we can capture two famous settings, namely the i.i.d. setting, where we assume that at each time step, the pair STMBT is drawn i.i.d. from a fixed but unknown distribution, or the adversarial setting, where we assume that at the beginning of time, there is an adversary that kind of writes on a slip of paper all this sequence of T pairs, and this sequence does not need to have any particular structure. Also, and this is what I already said. In particular, if you come from like approximation algorithm, it is important to note that what we are getting is not a multiplicative approximation. So we are not saying, okay, on the long run, we're getting a 2 approximation. What we are saying is that you give me any precision, I can get to that precision. So it is an additive error. So I see that there is a question.
Yes. Hi. So one clarification on the adversarial setting. Do you assume that the adversary chooses the sequence before or after the agents make a choice? So let me be a bit clearer. Suppose so is it first adversary and then agent, or first agent and then adversary in the timing of
Okay.
actions?
Okay, thanks for the question. So in these two types of agents are often called the oblivious adversary and the adaptive adversary. So in the oblivious setting, then this is exactly what I described. In the adaptive adversary, what happens is that we can imagine that this adversary at each time step kind of decides on the new pair. This adversary can know the algorithm that the learning agent is using, but does not have access to the random bits of the agent.
Okay.
In particular, what we are going to do, and this is kind of a bit of a spoiler, clearly the oblivious setting is the weaker adversarial model, but we're going to prove that this is already enough to prove a very strong impossibility result. So thanks for the question. And these are our results. Now in the stochastic setting, so when everything is i.i.d, there is a distribution, but we do not know the distribution, then we devise a learning algorithm that gets square root t regret rate, and we further prove that this regret rate is tight. And second, for the adversarial setting, even the oblivious one, that is the weaker adversary that we could think of, then we prove that learning is not possible. So namely, no learning algorithm can achieve sublinear regret. So actually, we get something stronger. We prove that there is a constant, I don't remember, like 3/2, such that no algorithm can get a 2/3 approximation of the benchmark in the adversarial setting. Okay, before going to the technical challenging, let me say something. So maybe you have never heard about online learning, but maybe you know something about sample complexity. Now, I do get that, like, if you've never worked on it, these square root t, omega t rates are kind of like magical numbers there. But the way I think about it, these rates kind of give you a qualitative hint on the difficulty of the problem. So in particular, you get square root t regret even when you are trying to do something as simple as learning what is the best one between two coins. So you know that one of the two coins is a Bernoulli with probability 1/2, and the other is a Bernoulli with probability 1 plus minus epsilon, and you do not know which one is epsilon. So even in this super simple setting, you cannot do better than square root t. So this kind of very complicated learning problem originated by mechanism design is actually as easy as finding the bias of a single coin. So this is kind of, at least to me, to us, when we discovered it, was kind of puzzling. Let me also tell you why this problem is interesting from the technical point of view. Now, if you have some experience with online learning, you may know some of the basics. And in particular, what you typically can handle with the standard tools is either a situation when you have a finite action space. So maybe you've heard about bandits or expert. So what happens is that you have, I don't know, you have k actions and you want to find which one is the best. Okay. But here you will have something that depends on the number of actions. Now, in our setting, we are kind of get the best mechanism. And the mechanism space is not only infinite, is not only continuous, is not even parametric, because it's like all the blobs that have this monotone structure. Now, the second kind of standard trick that you may want to use, you could try to exploit the regularity on the function that maps action to reward. or losses. So for instance, in line convex optimization, you may have a domain that is complicated as you want, but you have like a strong assumption on the functions that you're trying to optimize. So namely, they're either convex or they're strongly convex, or maybe you don't ask that, you just ask that they're Lipschitz. So they are like continuous with like a constant Lipschitz parameter. Now, actually, this is not the case for our problem. And this is kind of simple if you think about it. Now, imagine that you have like a super simple distribution. So this is the square. Here you have the valuation of the seller. Here you have the valuation of the buyer. And let's say that the distribution is extremely simple. It's like a unique point here. Now, if you have a mechanism that kind of takes this point, you will get constant profit. On the other hand, if you get another mechanism that maybe is like extremely close, but does not get the point, so something that is extremely close, but you miss the point, then now the profit drops to zero. So you see, even though in the, let's say, the domain space, you can be arbitrarily close, this profit function is highly non-continuous. It's highly irregular because it goes from zero to constant. Okay, so this is just a way to tell that the standard tricks do not work, so we need something more. And beyond that, let's try to use the standard toolbox that you typically have at your at disposal in these situations. The first idea is to say, okay, everything is complex, but if I can find a suitable discretization of the mechanism space, such that the best mechanism in this discretization is kind of close-ish to the optimal mechanism overall, and I can kind of learn easily all the mechanisms in this discretization, then maybe I can get something out of it. Okay, so here the idea is to say, let's just try to find a meaningful but fixed discretization of the space, and let's try to learn the best mechanism in that discretization, and then see what happens. And this is kind of what works, for instance, for pricing. So there is this paper by Kleinberg, Lighton, Fox 03, that is simply this. You just cast a grid and then play bandits on the grid. Now, it turns out that this approach does not work. And actually, we can say something stronger about why this does not work. So you give me any fixed discretization of the mechanism space that kind of, you may think it corresponds to a discretization on the valuation space, and then a mechanism is just, I don't know, a path that goes from here to here in this discretization of the valuation space. So if you give me any discretization, any fixed discretization, so let's say any grid in the valuation space, and you only consider mechanisms that live in this grid, then I can always find a distribution that breaks this discretization. Namely, I can always find a distribution such that the best mechanism overall gets, I don't know, one half, while the best mechanism on the grid gets 1/4. So you have this additive constant factor that kind of tells you that you will never be able to do sublinear regret, because you will always suffer constant regret over and over and over. And actually, the example is fairly simple. You just set a delta. You just set a delta that is like smaller than the precision of your grid, and then you consider the uniform distribution in this segment. Now, the best mechanism overall will be the blue one, so the one that allocates in that rectangle, and in that setting you always get a trade, and you extract the largest profit from each one of these realizations. On the other hand, if if you are committed, if you are constrained to only find mechanisms that live on this grid, so for instance, if you do something like this, then what happens is that you will always lose a lot of trade opportunities, namely, you will always lose these guys here. And you will also lose a lot of profit here, because remember, your payment will be like the difference between those two projections. So you see the y projection of all these points onto the green horizontal line will be far from their actual coordinates. So this simple example tells you that a fixed discretization does not work. And actually, with some work, one can embed can use this kind of structure to devise an instance that is impossible to learn from any learning algorithm. So in particular, we get this adversarial impossibility result that says that it does not matter. You give me any learning algorithm, I can always come up with an adversarial instance that breaks your algorithm. And in particular here, the phenomenon that we are using is the so-called needle in a haystack, meaning that we are hiding this super tiny delta that you cannot learn in the adversarial setting. So take home message, fixed discretization does not work, and we can actually tweak this hard example to get an impossibility result for the adversarial setting. So now let's try to understand what we can do in the stochastic setting. Remember, in the stochastic setting, we have a distribution, we observe samples from this distribution, and we want to learn the best mechanism. Now, the first natural attempt in this scenario could be to get some kind of pack learning result, meaning that you would like a statement that says something like, for any precision epsilon, there exists a number of samples n of epsilon, such that if you get n i.i.d samples, you can estimate correctly all the mechanisms. Actually, we have a super simple example where this is not possible for bilateral trade. Namely, just consider the uniform distribution between this point here and this point here. So 0, 1 half, 1 half, 1. And consider the segment that joins these 2 points. And consider the uniform distribution along these 2 points. Now, it does not matter how many points you will give me on this segment. What I can always do, I can always find a mechanism that kind of avoids these points while being super close to the diagonal, to this segment. So actually, to contain nearly every part of this segment. So this means that even if you give me 1 billion points, or does not matter how many points you give me, I can always find a mechanism with empirical profit 0, but whose expected profit is constant, because it's kind of it contains many of the nearly all the segment. Okay, so this does not work. What is our approach? Well, our approach is to find a class of mechanisms that it's the sweet spot between complexity, let's say, and approximation. And this is the class of epsilon simple mechanisms that are defined as follow. A mechanism is epsilon simple if its boundary is made up of order of 1 over epsilon axis aligned segment. So as simple as this. You just you can have whatever shape you like, but the boundary has to respect this feature. It's just a concatenation of horizontal and vertical segment, and there is like a complexity parameter that is epsilon, so that like you have order of 1 over epsilon kind of corners into this. Now with this family of simple mechanism, one could see that it's fairly easy to get a discretization error. So what do I mean by that? Well, imagine that you have any mechanism. So in particular, the mechanism here that you have here in blue. Well, if I cast an epsilon grid and then I kind of follow and I kind of get this outer hull of the boundary that lives onto this grid, so something of this form, then I get something that clearly will be epsilon simple. So I will have this m hat that is indeed epsilon simple, because it will have, I think, 2 over epsilon corners. But on top of that, I have a good approximation result, a good discretization error. Why? Because, well, for any point that is inside the blue region, so if the agents declare this point, then both the blue mechanism and the red mechanism gives rise to a trade, but the difference is profit is order of epsilon. Why? Because like the blue mechanism will pay this to the seller, while I will pay, like the discretized mechanism will pay this price here, that is epsilon close. While the buyer, well, in one case, the buyer will pay this, while in the other case, it will pay slightly less. So overall, for any point that is, any bid that is inside the blue allocation region, I get the same profit up to an additive order of epsilon. While for all the points that are outside the allocation region, then I'm happier because I don't care. So overall, for any mechanism, there exists an epsilon simple mechanism that provides an additive epsilon approximation. So now this is the class of mechanisms that we want to learn. Let's start with a warm-up. The algorithm is as follows. You are at time t, you have observed t samples, and you can compute the empirical, you can compute the best mechanism on these samples. But then, to avoid overfitting, since we know that we do not have uniform convergence, what we do, we propose a mechanism that is epsilon simple, that approximates the empirical maximizer. And this mechanism will just be like the, let's say, the doppelganger of the mechanism that lives in the order of 1 over epsilon t grid. So now the question is, what is the convergence rate that we can guarantee? So, I mean, in a certain sense, we are reducing the problem to an offline problem. I give you t samples, what is the precision that you can achieve within this family? Okay, so let's start to do some math. If I have t samples, then it means that I'm only interested in learning the epsilon simple mechanisms that are induced by these samples. What do I mean by that? So this is the square. Maybe, I don't know, I have this point, and this point. I don't need any mechanism. I need the mechanism that kind of was corner, depends on this on the realized point. And on top of that, I will also need a uniform epsilon grid to ensure that you have the coarseness needed for the approximation. So if I give you t points and I look at the grid induced by these t points plus the standard epsilon grid, then this is basic combinatorics. You can get that there are epsilon of log t over epsilon such mechanisms. So what you can do, you can just union bound onto this family. So you can prove that the error that you make in this class of epsilon simple mechanisms will be at most square root of the log of the cardinality of this mechanism divided by t. And in particular, since the cardinality is exp of log t over epsilon, you will get log t over epsilon here. But here there is a caveat. This is kind of technical, but it's I think cute. Now we are using the points we have seen so far to both decide, to kind of both do learning, but also to decide what is the family of mechanisms I'm union bounding over. So in particular, you see in the kind of sketch that I was drawing earlier, this is like the first point that arrives, the second point, the third point. Now, these points do not only appear here when we kind of compute the empirical frequencies, but they also appear in the family we are union bounding over. So here one needs to be really careful to avoid kind of this strange dependence between the family you are trying to learn and the samples you are using to learn this family. But beyond that, this is the sample complexity that one can get. Now, let's see how this sample complexity would help me. Well, the performance of the optimal mechanism. Well, this is well approximated by the by its empirical profit. Why? Because it's just one mechanism. So we can always assume that we learn it and we lose like log t over t. Okay, fantastic. We make this error and we estimate it correctly. Now we look at the samples and we look at the empirical maximizer, that is this guy, and we can compute it. And then what we actually play is not the best mechanism, but is the discretization of this best mechanism. That is this guy here. And in going from here to here, we have to pay this extra order of epsilon that is given by the discretization. And finally, here I use uniform convergence, the uniform convergence bound that I've proven up. And in particular, here is where the error term kind of appears. Okay? And then at this point, I'm free to choose epsilon because this is kind of the learning rate that I have. And if I set epsilon to be t to the minus 1/3, I get a t to the 2/3 regret bound. Now, what this tells me, what this kind of chain of inequality tells me, is that if I want to get square root t, then what I need to kill is this yellow term here. So I want to kind of get rid of this epsilon here, because if I do it, then I get square root t. Okay, so this is the next thing we need to push for.
Okay. Federico?
Yeah.
Just quickly, can you go back? Can you remind me what the issue is with the empirical optimal mechanism? I think I lost track of why we need to replace it in this case with the...
Yes, because what we know is that we do not have we do not have uniform convergence.
Right.
So this means that you see on sample, maybe there is a mechanism that is fantastic, but you do not know any way of assessing whether what you are looking at is kind of a crazy error in the distribution, or it's actually because this mechanism is good indeed. So this is kind of to avoid overfitting. So since we do not have uniform convergence, we cannot kind of commit to this super complex mechanism. So what we need, we kind of take a step back and say, okay, let's try to reduce everything to epsilon simple mechanisms.
Okay, very nice.
Awesome. And now the extra ingredient we needed is this kind of esoteric argument from probability that is probabilistic chaining. That is, like, very simplified, is a smart way to do union bound. So instead of just doing union bound with the same precision, with the same event for all the mechanisms at the same time, it's a smart way to kind of divide the union bound. So let's get into it. Now, we define for any mechanism M, we can define a sequence, a chain of successive approximation of such mechanism. So this blue one is the target. And here I will have phi 0 of M that only changes in, no, let's This is phi1. Phi1 of m, that is like a fixed price mechanism. You just post this price and see what happens. Then you can have, I think this is phi2m, this I think was phi3m, and so on and so forth. So at like the phi hm is just the approximation of the mechanism when the underlying precision parameter epsilon is 2 to the minus h. So you see this plot kind of shows you how you can get from a fixed price mechanism to kind of something super, super adherent to the actual boundary of the mechanism. Okay, so this will be kind of the chain that we're doing the union bound over. So in particular, for any target mechanism M, we can decompose its profit as follows. We just use a telescopic argument. So we have the profit of the first element of the sequence plus the profit of the first minus the profit of the zeroth plus the profit of the second minus the profit of the first, and so on and so forth, up to a certain precision epsilon. So after log 1 over epsilon steps. And I know that if I am a precision epsilon, I'm just making an error epsilon, so we are happy. Okay. And for now, let's make the simplifying assumption that for any mechanism M, you can find an epsilon simple mechanism where epsilon is 2 to the minus h, such that you have two-sided error bound. This is a simplification assumption, and I will lift it later. Now, if this is the case, then I can move from like the error that I make overall to the error that I make in each term of the summation. So let's say level by level, what is the error that I make? So in particular, the error that I make at the hth level will be upper bounded by the worst pair of mechanisms in that level. And here you see here I have like the empirical difference, the empirical gap between the mechanism at level h+1 and the mechanism at level h. And here you have like its expected value. So what you're trying to learn. And now here is where the magic happens. Why? Because now I have that I still have the standard Chernoff bound. So I have square root, of log the number of elements I'm union bounding over, divided by t. But now I have the term that kind of tells me what is the scale of the random variables I'm kind of trying to control. And given the simplifying assumption, this is the scale. This is the scale parameter. And this, like all the parameters are set in such a way that at the end of the day, I only get a dependence on h that kind of plays in my favor. Because it's like, I get square root of log t over t times this 2 to the minus h. That is something nice, something small that I can handle. Okay. So long story short, assuming that I kind of have a bounded difference property between one level and the next one, then I can kind of do union bounding only in that level. But since I know a way to control the scale of the random variables, then kind of the exponential dependence on h given by the cardinality of the family is killed by this exponential term that appears in the scale. Fantastic. So this is what we get. In particular, now, if I get to kind of the our goal, so kind of getting a uniform convergence bound for the epsilon simple mechanism, I can decompose the error with this summation. I can apply Jensen inequality and everything works nicely. And so the error that I make along a sequence is just the sum of the errors that I make in each level, in each one of these levels of approximation. So I have this telescopic summation that instead of like hurting me because I'm adding terms, it's kind of good for me because I can bound each one of these terms separately. So at the end of the day, I sum up all these error terms, but this is a geometric summation, so I get exactly what I need. Okay. So in particular, if you remember the calculations we did with the suboptimal algorithm, now we no longer have the epsilon, so we're happy. Okay. Now let me just say something super quick about this simplifying assumption. In general, it is not true that we have this two-sided error. If you remember, we proved only a one-sided error, meaning that like if I have a mechanism and an epsilon approximation that is kind of close to it in the outer, from the outside, then I know how to bound one-sided error, meaning that the profit of the outer mechanism plus epsilon will be an upper bound on the profit of the inner mechanism. But in general, you don't have the inverse inequality. So kind of what we did here is technical, but it's, I think, cute. What we prove is that if an approximating sequence violates this two-sided condition, then this is a witness that the last term of the chain is not optimal. So we can kind of avoid uniform convergence along the chains that exhibit this that do not respect the simplifying assumption. So what actually this tells me is that we get the square root t result, but this is not a let's say pack learning bound that tells me that with I don't know 1 over epsilon square samples I get an epsilon estimate of all the epsilon simple mechanisms. I just say that with 1 over epsilon square samples I can find a mechanism that is an epsilon approximation. So this is weaker, but this is exactly what we need. Awesome. So this is like high level the technical contributions of the paper, that technical outline. I will be more than happy to discuss it further. But before, let me just conclude with some observations. So what we did, we kind of studied a non-parametric mechanism design problem that surprisingly can be learned as easily as learning the bias of a coin. So you get a square root t rate. And this is achieved by doing probabilistic chaining combined with this discretization of the space that depends both on the data that I see and the distribution. Because clearly the distribution is the one that kind of decides what are the chains that violate the simplifying assumption. And also, if you kind of look at it from the AGT perspective, I think it's super nice that this approximating sequence, this notion of approximating sequence, it kind of fits very well in all this line of work in like simple versus optimal mechanisms. Because if you think about it, what you're saying is like, for any precision, I can find a mechanism that kind of gets this precision. And if I concatenate these mechanisms, I kind of exploit the specific structure to do union bound in a nice way. So like practically, this mechanism here, this is just a fixed price mechanism. This guy here, it's not a fixed price mechanism, but it's kind of, it's a, let's say, convex combination of fixed price mechanism, of few fixed price mechanisms. Okay, so this I think it's fairly nice. Perfect. Now, future directions. First, this construction can be generalized to other problems. So in particular, we had this EC, I think, 24 paper on a similar problem that was called the joint SAS problem. And with the same technique, we get the same tight result. And now what I think is really like the nice next question is try to understand whether we can get square root t also in the smooth setting. So what is the smooth setting? You are not assuming that the distribution does not change over time. So at every day the distribution can change, but it cannot be too peaked. it cannot be, I don't know, a mixture of deltas. It has to do some kind of uniform time scaling something. And there are many instances in problems arising from algorithmic game theory, where like in the adversarial setting, you cannot do anything, but if you add smoothness, then the problem becomes as easy as the stochastic one. So that's it. Thank you for your attention.
Thank you. Thank you. Yeah, time for questions. Feel free to unmute yourselves and ask any question.
Maybe, okay, I'll go for another one. So do you think this framework can be generalized to the case with many buyers and many sellers, or better, to what extent it can be generalized?
Okay, that's a great question. Yes. So the game theoretic characterization will still hold to some extent, but then visualizing and working with general mechanisms will be a bit of a mess. Because now already here with one seller and one buyer, we are looking at all the curves in a two-dimensional space. So what happens if you raise dimension, you get something that has more dimensions. So you will likely suffer to some kind of curse of dimensionality. What I think is that it's fairly easy to get some result, but getting tight results will become fairly complicated. Let me mention that actually for bilateral trade, there is a paper by Babayev and al. That is, I think, is C24, where they actually study efficiency maximization, so gain from trade, in small market, namely, I think, 2 sellers and 1 buyer. And already there, the situation was fairly complicated. So you need extra assumptions to like approach the problem. But I think that is extremely interesting, and there are good results to get out of that.
Thanks.
I was wondering, are there, so I'm not so familiar with the mechanism design literature, but are there notions of approximate dominance strategy implementability that people use in these settings as well?
Yeah, that's a great question as well. So we started with this with the notion of dominant strategy incentive compatibility that is the strongest possible. Now, let me get back to it. We are nearly there. Okay, here. Now, one could think, what if instead of dominant strategy incentive compatibility, I only have bigness? So this is Bayesian incentive compatibility, meaning that truth telling in expectation is the best thing to do. In expectation with respect to what? Well, let's say in expectation with respect of the mechanism designer randomness and the randomness of the other agents. Now, in this setting, you inherit the impossibility result by Meyerson and Satterthwaite because they are like obtained in this broader setting. But what breaks is the characterization of mechanisms. So in particular, you may have mechanisms that are big that do not respect this structure. In particular, there is the mechanism that gives you constant gain from trade. That is fairly simple. It's just you flip a coin, then with probability P, you ask the seller what is the price that you want to post to the buyer, and you post that price. Otherwise, you go to the buyer and you ask the same thing. Now, this mechanism, it's not clear how to capture it with this allocation region argument, even with the revelation principle. So even if you kind of ask both agents what are their valuations, and then you kind of run this mechanism. And let me also add something here, because I mean, this is a question we have investigated. When you move from dominant strategy to Bayesian, then what happens is that the mechanism that you want to prove, it's kind of expected to know everything about the distribution of the agents in order to be robust with respect to misreporting. But this is difficult in learning, because in learning you typically do not have the distributions of the other agents. So things become trickier. What one could investigate is to say, okay, what if the agents are epsilon big? For like an epsilon that decreases with time, what can I get out of it? So this is definitely a meaningful question.
Hey, thank you. Any other questions? Okay. So thank you again.
Thanks.